In this video, I'll be going over our intro again to functions, but with our part 2. So we're going to start today by looking at when a function can be tested out using the vertical line test. So remember, we defined a function as a relation in which every input x has only one output y. So if you're just given a graph and you're asked to determine is this a function, you need to see if it can pass the vertical line test. So we draw a vertical line through our graph. So when we talk about our graph, right, we have our x and y axis in the background. That is not part of the actual function or relation. However, the function or relation is this like blue line in these two examples. So it's the thing that's actually been put on the graph using our x and y values that are not just the x and y axis. So they've been points that have been connected together. So when we're talking about is this a function, we're talking about this kind of curvy line in both of these. So for the first one, I'm going to draw a vertical line just in a random spot, right? I notice right away that my yellow line here is touching my blue graph, right? But it's only touching it at one point. If I just pick up my vertical line and draw it in a new location, again, I'm still only touching one point at a time on my line. However, when I go to the next one and I draw a vertical line anywhere on my graph, if I draw one here, I can see it's only touching one point. If I draw one a little bit further over, here it is touching 2 points. So see right here where we have now touched our graph in two locations with that vertical line. So these two are showing two different things. The first one only touched my function at one point at a time. So this is a function because it used the vertical line test and only touched one time. But in our second one, when we drew a vertical line, we noticed that it is crossing through at two different points on the function. So this is not a function, it's just a relation because it did not pass the vertical line test. Now we're going to look at how we can graph linear functions. So when we talk about the word linear, we see the word line hiding inside of it. So a linear function will create a line. I've got two examples right below here for you. See how they're both creating that blue line on the coordinate plane of x and y axes. So in the first example, it says plot the points given below onto the coordinate plane. Then circle the points that lie on the line. So I've got these 5 sets of points. We reviewed how to plot ordered pairs last video, so go ahead and pause the video and try plotting these on your own and press play to check your work. We've got our points here at 1, 8, 0, 8, 2, 10. We've got -3, 5, and -2, 6. So 4 of them actually ended up being right on that line that was given to us, right? But we've got this one lone point out here that is not touching the line, it's just somewhere else on the coordinate plane. So the one that didn't actually end up being on our graph was this point 1, 8. So what we would say is that the other 4 points are on the graph of the line, but this ordered pair was not on the graph of the line. In the next example, it says to fill in the table using the points that are plotted on the graph of the line below. We have our first point here. We notice that it is 3 spaces to the left, so at -3 for the x value, and it went 2 spaces up from that origin. So -3, 2 is the first point. Go ahead and try to list the other points and press play when you're ready to check. The next point that I see is 2 spaces from the origin, and 2 spaces to the left of the origin, so -2, and it's up 4 spaces. So we have -2, 4. Then we have a point that is 1 space to the left of the origin, so -1 for x, and up 6 spaces on our y-axis. The last point is on the y-axis, so we did not move at all on our x, which is 0, but we went up 8 spaces on our y-axis. So all 4 of these points, or ordered pairs, are going to be on the graph of our line. So we're looking at that because you're going to see questions like this, where you're given a function rule. So on this next one it says, we have y equals 6x. That means that's the rule that is getting you a y value for every x value. So we want to know, are these specific ordered pairs going to work for that linear function? Are they going to lie on the line? So when we don't have a graph, we have to check that using our evaluating expressions rules that we've learned in the past using GEMDAS. But when we talk about them being on the line, it's because they actually do lie on the line if you end up graphing them like we did up here. So that's what we're asking when we say that. So we're going to look at the first point here. It has -9, -3. Remember, this is just an ordered pair written as x and y. The rule that we're asked to identify is to get y, you're doing 6x. Well, what does 6x mean? When a number sits next to a variable, remember there is that hidden multiplication in between. 6 is the coefficient on x. So we're going to be multiplying every x value by 6, and that should get us our y value. If it does, then these points are on the line. If it doesn't get us that y value, then that means this point would not end up on the line. So let's test this out. In our first one, our y value is -3, and our x value that we want to enter is -9. So y should equal 6 times x. My y value is -3, and my x value is -9. So -3 should equal 6 times 9. Well, 6 times 9 is -54, and -3 and -54 are definitely not equal, so this point would not be on the line. So that's kind of like the one that we saw up here, where it was on the graph, but it didn't actually lie on the line that we were talking about. So it would not be part of this linear function, y equals 6x. We can look at the next one, test it the same way. Our x value this time is -4, and the y value that's with it is -24. So we'll use our rule, y equals 6 times x. This time my y value should be -24, and my x value is -4. So -24 should equal 6 times -4. That answer is -24. Since those two values are equal, then we can say yes, this ordered pair, x, y's, would fit on this linear function because these x values made this y value. So that would be something more like this point where it was right on top of the line. It is part of the linear function. Go ahead and try the other two and press play when you're ready to check your work. Here we're seeing that we want to take y should equal 6 times x. Our y is 30 and our x is 5. 6 times 5 is 30, and since 30 equals 30, this point, 5, 30, will be on our line. In our last one, we have 6 and 12. So y should equal 6 times x. This time my y value is 12, and my x value is 6. Well, 6 times 6 is 36, and that does not equal 12. So this point would not be part of that linear function on the line. In our next example, it says which table represents the function rule y equals x minus 4. So we're doing something very similar to what we just did in the last problem, but this time we're given a table of values and we're comparing that to a potential function rule. So these two tables have x and y values, but we want to see which one came from taking your x value and subtracting 4 to make your y value. So we'll go ahead and plug in all of our x's and y's. If this rule works, then y, which in the first table is 2, should equal our x value of -2 minus 4. -2 minus 4 is -6. Since -6 does not equal 2, then this point would not be on this function rule. Therefore, the rest of this table is not going to work because every single input needs to get an output from the same exact function rule. So this one will not work for us. Let's test out the next one. So the rule that we want it to work as is y equals x minus 4. The y value I'm given first is -7. That should equal my x value of -3 minus 4. -3 minus 4 is -7. And since -7 equals -7, then I know that that row worked. However, just because one row works doesn't mean the rest of the table will work. So you always want to go through and check the rest of the points. -5 equals -1 minus 4. And that is true. -5 does equal -5 there. Then we have a y value of -2, which should be x of 2 minus 4. 2 minus 4 is -2, so that one worked as well. And we double check our last one. The y value is 0. Our x value is 4. 4 minus 4 is 0. So since 0 equals 0, we know that that would also work. So that means that this table is the one that contained points that represent this function rule y equals x minus 4. Every single x value when it was plugged in gave us the y value in the table when we subtracted 4 from it. In the next example, it's asking us the same thing, but it's just looking a little different. It's saying, which function rule does this graph show? So rather than being given the points, we need to find the points off of the graph and then test them in the function rules that we are given. So my first ordered pair right here is 5 spaces to the left of the origin, so -5, and it's 3 spaces up on the y-axis. So -5, 3 is one of the points that we're going to test out. The other one that should work is -2, 6. So these are the two ordered pairs that we're going to plug into our function rules. We have x's and y's, and we're going to use them in these two that were given to us as options to see which one algebraically works. So we're going to start with y equals x minus 8 here. My first y value that I see is 3, and the x value that went with that was -5. So let's see if we get 3 when we take -5 minus 8. -5 minus 8 is -13. That did not get us 3, so that means that to make this point, the rule y equals x minus 8 doesn't work for us. So that should not be our function rule, because once it doesn't work for one point, it's definitely not going to work for the entire function. So we can just rule it out, and we're going to move on and check the next one. So now we'll check the same x's and y's, but this time in the rule x plus 8. My y value again is 3, and the x that I'm using with it is -5. I'm going to add 8 to that. 3 does equal -5 plus 8. That gets us +3. So that point worked. So we're going to make sure that this point also works in the same rule. Because again, if not every point, like up in this table, if not every point of that worked, then it wouldn't have been part of the function. So we always want to double check that once one of them works, check the rest of them. So now we're going to use the same rule, y equals x plus 8, because that worked to the first one. Plug in our other y value of 6, the x value of -2, and plus 8. -2 plus 8 is 6, and that's what we were expecting to get from our ordered pair, so we know that that one also is going to work. So that means that the line on this one can be represented with the equation or the function rule, y equals x plus 8. Any other ordered pair that you would find on this graph should get you, when you take your x value, you should be able to add 8 to it to get your y value. So in our last problem, it's very similar to what we just did. We're looking to see whether this table matches the graph. So we were given a set of ordered pairs. We are going to see if they lie on the graph of this line. We'll look for the first point of -6, 4. So we go 6 spaces to the left and 4 spaces up. That is right there on my line, so far it matches. We need to check all of the points before we can say yes or no definitely. -4, 2, we're going to go 4 spaces to the left and up 2. That point worked. 1, -3, we go 1 space to the right and down 3. That point is also on our line. Last point we have is 7, -9, so we're counting 7 spaces to the right and 9 spaces down, and that does indeed lie on our line. So we didn't get any points where it was sitting way out here off of that graph of our linear function. All 4 of those ordered pairs that were in the table were directly on that line on our graph, so we can say that this table does match the graph of this function rule.